last 2 weeks, we talked about descriptive statistics. Well, we started out with introduction to statistics, and then we moved on to descriptive statistics. So as a brief review, I would like to go over some important points that I believe are crucial for us to continue on with this course. So the first thing is the scales of measurements. If I recall correctly, a bunch of you also mentioned in your weekly reflection that this is something new that you didn't really pay attention to before. I'm not saying that it's something that you didn't know before, because I think it's probably common knowledge, but perhaps you didn't put much thought into it prior to this class. So when we are measuring anything, when we are taking measurements of a certain variable that we are intending to study, we can measure it in different ways. And as we go down these options, we get more and more precise. If you recall, all of these scales have the property of mutual exclusivity, which means if one measurement is, for example, the value is 3, there's no way that it can fall into another category or have a different measurement. So every single measurement is unique, and every object that is measured will have a unique value or a unique measurement. So this is valid for every single scale. But for the nominal scale, we stop there. There are no other criteria that needs to be fulfilled for a variable on the nominal scale. However, if we move down, we see ordinal scale. It starts to have another property, which is LO. Does anyone remember what LO stands for?
Logically ordered, ma'am.
Exactly. Thank you, Joanna. So logical order, logically ordered. So it means that from the different options or the different values that a variable could have, it has a certain order. So if I say you have a grade of A, you get an A for Statprob, obviously it is logically ordered, it's better than B, and so forth. Next, we have one more criteria, which is ED. Does anyone care to help me out on what ED stands for?
Equal difference, ma'am.
Okay, who's that? Yes, equal difference. So the main idea here is that between these ordered values, there is a standard of difference between those orders, those ranks. Like for example, if you say the grades of a certain course, A, B, C, D, E, you cannot really say that the difference between A and B is the same as D and E, for example, because they mean different things. However, if you talk about the interval scale, you have to maintain this equal distance between every single measurement you take. So for example, you can measure on the interval scale, you could measure temperature, you could measure what else? Different nominal things. However, here's the tricky part, because the one difference between the interval scale and the ratio scale is something called 0A, or zero of absence. So you can see here that the ratio scale has that property, but the interval scale does not have that property. So what it means here is that when you have a value of 0 on the ratio scale, it means an absence of measurement. It's non-existent. While on the interval scale, when you say 0, it just means that it on the number line, on the arithmetic number line, it's just a value, it's just 0. So that's why a lot of the times the example that can be used for interval scale is temperature. And honestly, at this moment, in this precise moment, it escapes me another example. So any one of you during the class, if you have an idea of interval scale, feel free to write it down in the chat box, or so that everyone can share. At the moment, I actually cannot think of another example. And everything else that you usually measure with numbers will most likely fall into the ratio scale, such as height, such as weight, and so forth. Maybe a thought. So now you have your scale of measurements. You go out and you measure UI students' heights, for example. So in the first step of doing any statistical work, you need to, it is desirable, I can't say need because technically you can skip this step. However, it's not really a good practice. So you first need to describe your data. So when you present your study in a paper, in your undergraduate thesis, you first need to describe your data sets. And then you need to give an idea or summarize them. Describing your data sets, we already looked over a bunch of ways to show graphs and to group your data. While when we talked about summarizing data sets, we talked about different measures that we could take from our data in order for us to get a better idea about our data. Recall that we have measures of central tendency, measures of variance, and measures of position. Once again, I'd like to assure you that memorizing these equations is not the point of this course. You have many tools. We are all computer scientists, which means you can use programs, you can use Excel. All of these tools are here to help you. However, you do need to know what these measures mean and have a general idea as how to compute them so that if your tool gives you a wrong number, a wrong computation, you should know that it is wrong because you are smarter than your tool. So up until now, we talked about taking measurements. So I would like to measure height, I would like to measure GPA or whatever. But when I'm measuring things, a lot of the times they will have different ranges. They will have different distributions. If you recall those shapes that we talked about, the distributions. So if we have multiple measurements, multiple variables that are probably measured on different scales, so it would be in some cases desirable for us to map them into the same scale. That way we can compare them easily. Like if you recall, I used the example about the height and my friend's height, where she looks a lot taller than me. However, if you consider the distribution of Indonesian females and the distribution of European females, obviously the height of our heights will fall into different distributions. And thus it would be possible for us to map two different heights or two different measures on two different scales. So if you look at it like absolutely, if you take an absolute value of these, obviously one is higher than the other. However, if you were to map them on the same scale, then you could see a more objective view as to which one is maybe more and which one is less. In this case, we use the standard deviation as a unit of measure. So what you are saying when you say 0.5 is your z-score, you're practically saying that, oh, this score falls 0.5 standard deviations to the right of the mean. If you have a negative, that means it will fall to the left of the mean and so forth. So as an illustration, we used this example last week. Aside from the heights, we also talked about different scores. Although we see here that the scores are, if you take the absolute values, that 83 in history looks really good. But when you consider the standard deviation and the mean of the three tests, you actually can see that the z-score of the math score, the z-score of the math score obtained is actually a lot better, because considering the mean and the standard deviation of that particular subject, 68 is not a bad score, where when you have 83 and everyone else has an average of 89, maybe 83 is not such a good score anyway. So here you can compare different types of variables on different types of scales and different distributions so that you have an objective view on all of them. So after we do that, we now have different measures of different types of variables. For example, I could ask each and every one of you, how many hours did you spend studying in 1 week? Then later on in the midterm period, I could measure all of the scores that you guys get on your Statprob midterm exam. So obviously I can measure the number of hours easily. I can just ask you and I can put the number on it. And for the midterm score, it's also a numeric number. I have two different variables here. However, a lot of the times in statistics, one value on its own doesn't really give us any information. So in order for us to get a higher level inference or a higher level knowledge on whatever phenomena this is, maybe I would like to study the correlation between these two things. Does more numbers of hours of studying correlate with a higher midterm score, perhaps? So I could use correlation concepts in order to study this relation between the two variables I have here. I can figure out the nature of correlation, if any, as well as the strength of correlation. For the nature of correlation, I can use a scatter plot to see in which direction the relationship goes. Like, for example, if you say here, if it's a positive correlation, it goes that way, it goes to upper right, it's positively, and on the other way, it is negatively correlated. And if it's a perfect correlation, it will be better, it will be closer to 1. And if it's not, no relationship, it should be closer to -1 and so forth. So here from the scatter plots, I can only get an idea of the nature of the correlation. But if I wanted to know exactly how strong the correlation was, I would need to use certain measures. We have two that we have studied in class. We have Pearson R and Spearman Rho. I'm not going to go over all of the formulas again because you can look at last week's material for that. However, we know that the Pearson R can be computed using 4 different types of formulas. And if we want to compute it, we have some conditions. We need to have some paired observations for every single data point. We have to have both, and it has to be measured in either the interval or a ratio scale. So for the factors that will affect the size of Pearson R, it's the linearity, how linear the relation is, the homogeneity of the group, if it's varied or not within the group, as well as the size of the group, because obviously we would probably get a different idea if we only have 5 people and if we have 500 people. However, one thing that does not affect the Pearson R is the magnitude of our scores. So if I were measuring GPA, that means the score would only have a range between 0 and 4. However, if I'm measuring height in centimeters, obviously it would be in the hundreds. So that is one quiz question that we had in our pre-test. So the magnitude of the number will not affect the correlation coefficient. In addition to Pearson R, we also have the Spearman Rho, which is a special case of Pearson R that can be used if we don't have the exact values of the measurements, but instead we have the ranks, like we know which one goes first, which one comes first and second and so forth. And it is an approximation to Pearson R. And the only thing that would make the result different is if you have tied ranks, if you have the same raw scores in the same, that come up more than once. So you have the rank 5, for example, you have 3 of them because all of them have the same raw score. And this is what is approximated. And that is where the Spearman Rho will give a different measurement, a different value than Pearson R. Okay, so that is the end of our recap. Any questions?